fiber reinforced concrete. Slide is not. Okay, why we need UHPC in India? Usually, actually, we have in our Indian standard code.
Share your screen first. Sorry, I have to intervene. Screen आपका फिर से चला गया. Please share your screen again. Screen is not visible right now.
Wait. Now able to see the screen?
Please put on slide mode, then I'll confirm. Yeah. Can you just, yeah, now it's moving.
Okay. The design of low-cost Indian ultra-performance concrete we are going to discuss today. Myself, Dr. Naresh Kalaskar, concrete division from Adani Group. I'm looking after special concrete division, Andhra Pradesh and Telangana. At present, we have in India, in our code, we have several design mixes from up to M20 to M80 we have. And why we need UHPC in India is a very important point which we are going to discuss now. So if you see the current challenges in India at present we have several challenges, infrastructural challenges I can say. So tall buildings and super tall buildings, long span bridges coming in our National Highway Authority of roads, and high-speed rail network. We are constructing bullet trains, hyperloop, and ceilings, underground tunnels. So many important structures, including military structures like blast resistant structures, missile impacting structures, nuclear power plants. So for these all structures, for these all infrastructural challenges, the normal concrete is not sufficient. So we need a concrete which is high performance, and it will give a excellent durability aspects. So for that, the ultra high performance concrete is an answer. So if you see, I'm taking the Hyderabad as a example. If you see in Hyderabad, we have reached up to 60-story buildings construction, super tall building construction we have reached. So this is becoming very common. If you see in Delhi, if you see in Mumbai, tall and super tall buildings and high span structures and hyperloop and many structures like where the infrastructures are throwing a challenge to civil engineers. So for this, we need an exceptional material, which is ultra high performance concrete. So in this presentation, we are going to discuss about ultra high performance concrete, how to reduce its cost, and how to use the local available materials, and how to make a exceptional concrete which will give an excellent durability aspects. So what UHPC gives if you compare with the normal concrete? So UHPC is a cementitious composite. It will give enhanced strength. If you see the normal concrete, it will give up to M60, M70, M80. But in ultra high performance concrete, from starting M100 to up to M200, we can reach, and long-term durability. If you compare with normal concrete, the UHPC give exceptional durability aspects. In this presentation, we are also going to discuss about the durability aspects at the end of the presentation. And UHPC, one of the important properties, tensile ductility. It is an excellent tensile ductility material.
Sorry to intervene, Dr. Sahab, one request. ये जो आपका नीचे स्टॉप स्क्रीनिंग के साथ में बटन दिख रहा होगा, उसको हाइड कर दीजिए, so that ये थोड़े से आप हाइड बटन जी उसमें हाइड लिखा हुआ है सर, उसे कर देंगे तो it will hide. Yeah, this bar. Now the whole presentation will be visible. Thank you.
Okay. The future of the concrete. If you see the future of concrete, now we are in 2025 and we are using up to M80 and normal concrete. If you see the future of the concrete, 21st centuries, the ultra high performance concrete will be the future, because high workability with zero honeycombing, there will be no honeycombing and segregation in UHPC, and minimum compressive strength will be M100, And traditional concrete tensile strength comes around 2.5 to 5 MPa, but in ultra high performance concrete, minimum tensile strength we can get 8 MPa, and ultimate flexural strength about 20 MPa, and modulus of elasticity 77,000 Newton per atmosphere. So the main principle of this material is high packing density. So if you design the material as such like that, the packing density, if you make perfect packing density and low permeability, definitely you will get an excellent material, and it will also resist the chemical attack, which is one of the important durability aspects. So you can see in this graph, the material in this graph, we have compared the UHPC, normal concrete, and steel. So you can see the UHPC comparison with steel and concrete, force versus displacement. Unique features, as I've told, with UHPC we can reduce the overall weight of the structure, and negligible low reinforcement steel, and low maintenance cost, and sleek and elegant looks, and ultra high wear and impact resistance. And we can get within 24 hours, we can reach up to 60 MPa compressive strength. Within 3 days, we can reach up to 100 MPa compressive strength. The principle of mixed combination of UHPC, now I'm sharing you. The 4 basic important mixed combinations principles are there in this. One is in UHPC, we have powder and fine materials. Second is super plasticizers. Third is fibers, and 4 is water. If you take the powders, in powders we are using ordinary Portland cement, and second is quartz sand and fine silica sand and ultra fine GGBs are the powders, and super plasticizers. Super plasticizers are very important for ultra high performance concrete, because in the normal concrete we used to take water cement ratio 0.4 or 0.3 water cement ratio, but in ultra high performance concrete we have to bring down the water cement ratio up to 0.15. So to get the proper fresh properties of concrete, we need an excellent super plasticizers. So super plasticizers plays a major role in ultra high performance concrete. And crimped steel fibers. Steel fibers are very useful and very, very important in UHPC, because in powdered concrete, if you take this high strength concretes, there will be a lot of shrinkage. And this crimped steel fibers reduces the shrinkage also. And it will also improve the flexural behavior, and it will reduce the shrinkage. So crimped steel fibers also plays a major role. And water as very, very important to make the mix. The main principles of this UHPC is there will be no coarse aggregate in the mix. So usually we used to add 20 mm aggregate and 10 mm aggregate in the normal concrete. But in the UHPC, in the Indian UHPC, which we have designed, in this mix, we have used 2.36 mm maximum size of aggregate. 2.36 mm is a maximum size of aggregate. And second principle is higher packing density and no weak layers, and steel fibers, which will improve, which I have told you, ductility and UHPC adding steel fibers and reduces the shrinkage also. And these are the main mixed combinations of UHPC. The principles of mixed combination of UHPC, of course. So in this UHPC, we are using cement as a binder. So if you use binder more than, if you use more binder, we will face the heat of hydration. So here we are replacing the binder with cementitious materials like silica fume, ultrafine GGBS, fly ash. So these are the options. But in this total study, we have not used ultrafine GGBS. We have not used the silica fume material. We have taken only ultrafine GGBS and fly ash materials we have considered to reduce the cost of the mix. As you see, the hydration process, when you take ordinary Portland cement, primary hydration will start, and 70% of lime will be hydrated with water, and another 30% of lime will not be hydrated. That will be hydrated with this cementitious materials. So if you see the UHPC and global scenario, in India we don't have any UHPC code, but if you see in every country, in each country, they have defined the UHPC in different way. If you go to China, they have defined the UHPC as a minimum compressive strength is 100 MPa. If you go to Canada, they have defined UHPC as 120 MPa is the minimum compressive strength. If you take ACI code, they have designed, they have defined 150 MPa is a minimum strength for UHPC. So in India, we don't have any UHPC code, and we have a guidelines up to M80. So that is the reason in this work, in this research, we have developed a UHPC from M80 to M150 to bridge the gap from Indian standard M80, M90. That's the reason M80 and M90 also we have designed in this total project. These are the materials used in the mixed design: ordinary Portland cement, ultrafine ground blast Francis slag, natural sand, silica fume. Silica fume has been tested but not used in the concrete. Quiet sand, superplasticizers, shrinkage reducing agent, crimped steel fiber, and water. These are some material properties. This is a cement material property where compressive strength of OPC 53 we got at 28 days is 58 MPa. And you can see all the regular mechanical material properties of cement in this slide. These are the natural sand properties. We have taken a zone 2 sand and quiet sand. Quiet sand we have used, and in starting M80 to M120 we have used natural sand. After M120 we have used totally replaced natural sand with quiet sand. These are the mechanical properties, material properties of quiet sand. So these are the materials which we have used: natural sand, quiet sand, ultrafine GGBS, crimped steel fibers, 53 grade cement, and high-end water reducing agents. Ultrafine GGBS. So we can say Alcofine. In Ambuja, we are manufacturing Alcofine. It's nothing but is ultrafine GGBS. These are the properties of ultrafine GGBS. You can see the specific surface area, 12,000 centimeters square per gram. It's one of the beautiful thing this material is having, so that we can reduce more voids. We can reduce the we can improve the packing density, and we can improve the concrete with more make the concrete more non-porous. Crimped steel fibers. So the crimped steel fibers density is 7,800 Newton per meter cube. And the aspect ratio is one of the important point in UHPC for fibers. The aspect ratio which we are using, which we have used in this design is 42.3 is the aspect ratio. Its aspect ratio is nothing but L by D, length and diameter of the fiber. So crimped steel fibers, definitely it will reduce the shrinkage, it will improve the flexural behavior, and it will reduction in place and cost and various wire mesh and for temperature and shrinkage control. These are some important advantages of benefits of crimped steel fibers. High range water reducing agent. We have used TEMSEM 53V high range water reducing agent. Water as per Indian standard. Drinking water we have used. So is expensive? Is the UHPC expensive or imported silica fume required in UHPC? So most of the designs if you see the foreign countries UHPC designs, they will use lot of quantity of silica fume. So silica fume is an imported material, and it is very, very expensive material. So is it required to design UHPC with silica fume? So in this coming slides, we are going to discuss how silica fume behaves when you use more quantity. So a small experimental thing we have done, where we have created a mortar cubes. In that mortar cubes, we have replaced the cement, 10% cement replaced with ultrafine GGBS, and 10% cement with silica fume. I think you people know about how to test the mortar cubes of Indian standard mortar cubes. Like we used to test for cement grade test for like 200 grams of cement and 200 grams of 600 grams of indoor sand. Like that, 200 grams we used to add the cement, and we used to test the cement compressive strength. So same thing, same study we have done. We have replaced the ultrafine GGBS and silica fume 10%, 20%, and 30%. And after mixing that, we have casted mortar cubes, and we have tested these mortar cubes at 3 days, 7 days, and 28 days. So these are the results which have got. So when we have added 10% of silica fume, we got 46 MPa compressive strength. When we have increased the silica fume to 20%, this compressive strength of 28 days has been drastically down, around 16.7 MPa we got. When we have added 30% of silica fume, the compressive strength at 28 days drastically down 8.5 MPa. So when you are increasing the silica fume content from 10 to 20 to 30%, the strength is coming down. But when you are using ultrafine GGBS, when you are using 10%, when you are replacing cement with the 10% of ultrafine GGBS, you are getting 59.9 MPa strength. When you are increasing 10% more of ultrafine GGBS, you are getting 63.4 MPa compressive strength. When you are replacing 30% of cement with ultrafine GGBS, you are getting 72.3 MPa compressive strength. So in this study, we can perfectly understand that silica fume is not suitable for ultra high performance concrete, and even it is a high costly material and it's an imported material. So ultrafine GGBS is abundantly available in India. We can use this material up to 30% in ultra high performance concrete, and we can reduce the cost and we can improve the performance of the mix. So this is a mixing procedure. In most of the people saying that UHPC required a special type of mixing facilities. Not at all required. In the common AML mixer, we can prepare the UHPC mix, but we need a good quality of admixture. So if you use a good quality of admixture, you need not require any special type of mixtures. So primarily, when you mixing the this mixture, first you have to add cement and fine powder material like quicksand. After quicksand, you have to add your total whatever powder material you are having, like silica sand and whatever this cementitious materials you are having. You have to mix it in dry condition. After mixing dry condition thoroughly, you have to add the water. After adding the total water, you have to mix it for 3 minutes. After mixing 3 minutes, you have to add slightly and slowly the admixture you have to add. And after, you should not add admixture totally in one time. You have to see the mix behavior. You have to see how mix is behaving when you are adding the admixture. So it's a total 7 to 10 minutes procedure. After when you are adding simultaneously, when you are adding water simultaneously, you have to add steel fibers also. So that the steel fibers will be perfectly mixed. So total mixing procedure will be around, the total mixing time will be around 10 minutes, so that you will get an excellent mix. So this is the M80 grade of concrete. In this, you can see we have done several trials. In trial mix 6, you can see this. We have added quicksand, medium quicksand, and natural sand. Medium quicksand and natural sand we have added. And if you see the trial mix 6, we have added same natural sand and quicksand. So we got this M80 concrete, we got 90 MPa compressive strength. So this is the final mix design for compressive strength of M80. So you can see here in this total mixing, we are same just like we have done a previous experiment. We are increasing.
Good morning, sir. आए हैं क्या? ठीक है, मैं आता हूँ फिर आधे घंटे।
Mr. Sunil, please keep yourself on mute.
के करीब आता हूँ मैं आपके पास। Thank you.
Hello. If you see the graph trend, when you are increasing the ultrafine GGBS, when you are increasing the ultrafine GGBS content, your compressive strength is going up. So when we have used ultrafine GGBS 20%, our compressive strength was 66.95. When you are using ultrafine GGBS 25%, our compressive strength was 90 MPa. So ultrafine GGBS or alcofine is a excellent cement replacing for UHPC. This is M80, and even you can see the water cement ratio here. When you are increasing the water cement ratio from 0.28, you got M80 strength 66.95. When you are reducing the water cement ratio, like for M80, we have used 0.18 water cement ratio. So when you are using 0.18 water cement ratio, you got 90 MPa strength. So in this graph, I want to say that ultrafine GGBS content and water cement ratio, when you are increasing ultrafine GGBS, you are getting more strength. When you are reducing the water cement ratio, you are getting more strength. So these are the very important factors which you have to keep in mind while designing the UHPC. So low water, higher good quality binder, and supplementary cementitious materials will be important. So as you know, in India, in Indian standard, we have a standard deviation up to M80 only. We have standard deviation for normal concrete only. We have for all higher grade concretes, code has specified only 5 standard deviation. So in M80, we have also calculated the standard deviation for all these mixes. We got standard deviation. We have established standard deviation is 5.56 for M80. This is M90. Same, you can see 103 MPa compressive strength we got. This is a design. The standard deviation for M90 is we got we have measured 5.85 standard deviation, and you can see the beauty of UHPC in this. Even after failure, the cube shape, you can see cube is perfectly intact even after the failure. So this is one of the beauty in UHPC. It will not fail whole. The cube will be, and the shape of the structure will be intact even after the failure. So this is M100. In M100 also we have used quad sand, natural sand. In this design, we have reduced the natural sand content and we have used quad sand. And when we have used quad sand, finer quad sand, we have got 112 MPa compressive strength for M100. The standard deviation has been established for M100 is 6.12. These standard deviations can be used because we have done an extensive trials for these mixes, and we have established these standard deviations. Around 30 sets we have tested for each standard deviation calculation. This is for M110. The compressive strength has been seen 122 MPa compressive strength. Here you can see.
presentation दे देंगे.
Hello.
Sorry.
In this M110, we have totally omitted natural sand, and we have taken quad sand, finer quad sand, and medium quad sand. So when we have omitted total natural sand and we have taken only quad sand, we got a compressive strength of 122.61. You can see here for M110, and we have established a standard deviation for this mix is 6.26. This is M120, and the strength has been. You can see here in previous mix we have used quad sand, finer quad sand we have used. In this mix we have used medium quad sand and coarser quad sand. Quad sand and finer sand, both the quad sand has been omitted, and only medium quad sand we have used. And when we have used only medium quad sand and also we have omitted natural sand, we got 131.66 MPa for M120. So these are the standard deviation for 6.34 for M120. M130, 142.09 compressive strength we got. In this medium quad sand has been used. You can see the compressive strength machine, 140 MPa compressive strength for M130 we got. This is a standard deviation calculation. One of the pick taken from my laboratory. This is a M140. You can see here in this mix we have totally replaced natural sand and finer quad sand, and we have used medium quad sand and coarser quad sand. And when you have used, we got for M140, we got 153 MPa compressive strength. This is a, have you understand? Are you observing the standard deviation is going up? When the mix, when the compressive strength is increases, automatically standard deviation also increases. For M140, we got 7.23 standard deviation. This is M150. In M150, we have used medium quiescent and coarser quiescent. And in this trial 6, we have used 50-50%. Medium quiescent 50%, coarser quiescent 50%. So what is happening? Here, you please understand, this coarser quiescent voids will be filled with medium quiescent. The medium quiescent voids will be filled with cement paste, and cement paste voids will be filled with ultrafine GGBS. So when you are planning your total density matrix perfectly, then only you can achieve the perfect compressive strength. In this M150, we got 164.06 compressive strength. So in this study, I have stopped till M150, and next I'm going to this M150 standard deviation 7.82. The M150 standard deviation. Small video of mix, how it is, what is the how the fresh properties of this mix you can see. Can you imagine what will be the water cement ratio for this? This is M150. Water cement ratio is 0.14 water cement ratio. At 0.14 water cement ratio, the mix is flowing like anything. We can make it as a pumpable also. Just we need to correct the admixture dosages. We can make it pumpable also. So usually UHPC will be poured like this only. If we need any pumping requirement also, we can change the admixture dosages. Then we will get the mix required fresh properties of concrete. So these are a few fresh properties of concrete test we have done. Workability test, V funnel test, L funnel test, flow table test we have done. Flow was good, and L funnel result was 1, and time seconds are 10 seconds it has taken, and the flow table was 15 seconds, and these are the few fresh properties of concrete testings as per ASTM C1437 and C1611. So we have done one more study on this UHPC, because usually in southern India, I have done my research in university laboratory, where we was having only 3000 kN machine, compressive testing machine, 3000 kN. So for testing M150 cube, we need minimum 5000 kN machine if you are casting 150 mm cube. So that is the reason I have done one more point. That is, I have reduced the cube size. I have taken 100 mm cube, and I have taken 100 mm cube and casted 100 mm cubes and 150 mm cubes. And I have taken external labs support where 5000 kN machine was there. And I have done a study. What will be the specimen? What will be the size effect when you are reducing the size of cube? What will be the effect on compressive strength? This study I have done. So if you see, for 100 mm cube, when you reduce the compressive for same mix design, when you are reducing the cube size, the strength will increase. But same mix design, when you increasing the cube size, the strength will be reduced. So with this study, I have established 2 multiplication factors, which can be used anyone in coming years, in coming research. If you are casting 150 mm cube, if you have casted 150 mm cube of UHPC, and if you want to convert those 150 mm cube results into 100 mm, you have to use multiplication factor 1.05. Whatever compressive strength you are getting, you multiply with this 1.05, and you will get the 100 mm cube results. If you have casted 100 mm cube, if you want to convert it into 150 mm cube, then you have to use multiplication factor of 0.96. So these are the multiplication factors you can use as per the requirements. So these are the multiplication factors we have used, and we have checked with the target mean strength. So splitting tensile strength. Splitting tensile strength study also has been done. Now I'm going to explain. So splitting tensile strength, we have a formula in code 0.39 under root FCK. If you take M80, if you multiply with this theoretical formula 0.398 under root FCK, the splitting tensile strength for a normal concrete will get 3.56 for M80. So with this UHPC, we have done a splitting tensile strength test. We got 5.33 splitting tensile strength values. If you take M150, splitting tensile strength as per code formula, we will get 4.87, but 9.8 splitting tensile strength we got for M150. This flexural behavior of ultra high performance using L box, this session I will take in some other time, because this is also one of the important study where the fibers plays a major role in improving the flexural behavior of UHPC. This is the flexural strength we have checked for UHPC on UTM, Universal Testing Machine, where M80, if you take M80, we have a formula in code that is 0.07 under root FCK. For M80, the value will be 6.26 as per code, but for UHPC we got 13.41. If you take M150, the code specified formula will get 8.57 flexural strength, but we got 23.87. We can say 24 MPa of flexural strength. So we can see the flexural behavior of ultra high performance when comparing with
Mr. Revant, please mute yourself.
So Young's modulus is one of the important factor, one of the important parameter for concrete. If you see, we have also tested Young's modulus, where we got for M150 77 GPa Young's modulus we got for M150 concrete. These are the mechanical properties which we have tested. This is one of more single table where I'm showing all mechanical properties. Compressive strength. This is the top row is a target mean strength. So below is the experimental result. So we got the target mean strength 162 MPa for M150. We got 164 MPa compressive strength. Flexural strength we got 8.57 as per code. We got 23.87. And splitting tensile strength as per code we have to get for M150 4.87. We got 9.76. And Young's modulus for M150 we have to get 61,237.24, but we got 77,080. So these are the exceptional properties of ultra high performance concrete made with Indian materials, with low cost materials. So these are the durability tests. I have performed durability tests like water penetration test, chloride ion penetration test on UHPC specimens, and you will surprise after seeing the results of UHPC durability parameters. M150 has water penetration of 1 mm. So if you see the code IS 16700 2017, the foundation maximum water penetration should not be more than 15 mm. Superstructures maximum water penetration should not be more than 20 mm. So for M150, we got 1 mm water penetration in water penetration test. Rapid chloride ion penetration test. For M150, we got 155 coulombs, which is a very low penetration when comparing with as per table given in the code. So with these two parameters, water penetration and chloride ion penetration levels, we can say this ultra high performance concrete is an ultra durable concrete. These are some photographs of RCPT testing. In the coming days, we will also present flexural behavior of ultra high performance concrete beams. These are some few photographs where I'm measuring the steel fibers, mixing the alcofine, and introducing the reinforcement cage in the beam. And one exceptional and good design parameter of this concrete is we usually the UHPC will be cured in heat curing, thermal curing, but we have cured these all specimens in normal curing at 28 degrees plus or minus 2 temperature. So for curing also you need not require any special setup. Just you can manufacture your concrete and you can cure it as per your site condition. You will get UHPC results. So gunny bags we have used to maintain the moisture. These are few photographs of beams which we have tested for M80, M90, M100, 110, 120, 130, 140, and 150. So this details about this study will come into the next presentation, because it will take minimum 1 hour for this presentation for this on this topic. So finally, confirmed with designs when you compare with the target mean strength, all the designs which we have designed from M80 to M150 with local materials, it has crosses the target mean strength, and all specimens have got exceptional results in mechanical properties and durability aspects also, in fresh properties also. These are the target mean strength and standard deviation achieved from M80 to M150. The standard deviation has been established, and these are the size effect factors. This is a cost analysis. If you go to Bombay, if you want to purchase a UHPC, you have to pay 80K to 1 lakh, 80,000 to 1 lakh rupees per cubic meter. Some reputed companies are selling at this price. So this whole concrete we have brought it down to 70% lesser than the market price. So if you are purchasing M150, you have to pay 80,000 to 1 lakh. So our designed concrete has brought it down to 28,366. This can be reduced some more by optimizing the binder content in the mix design, which needs extensive trials. So these are the conclusions. In these conclusions, all the materials, ultra performance concrete materials being materials which has been used in this UHPC has been tested for its physical and chemical properties. And 78 trials has been done for this M80 to M150 to establish these all strength. To establish these mixed designs, we have done 78 trials in the lab, and extensive study has been done. And standard deviations and compressive strength has been established along with size effect. And developed the concrete has given an exceptional results for flexural behavior, splitting tensile strength, and also has given an excellent Young's modulus. And one surprising thing I'll tell you, that the beam which has been designed with M150 has taken 60 tons of load in flexure. So this is one of the breakthrough which we have seen in this design. And durability properties also, we got 1 mm penetration water levels and 386 to 155 coulombs of chemical penetration. The cost has been reduced up to 70%. And how it has been reduced, now next slide we are going to explain. So how we made Indian UHPC a cost effective. No imported materials in the mix. So there is no silica fume in the mix. Higher percentage of binder replaced with supplementary cementitious material. So binder content has been replaced with alcofine or ultrafine GGBS, and we have not implemented any heat curing, and we have designed the perfect packing density by using 3 types of sand, like quartz sand fine, quartz sand medium, quartz sand coarse. So these 3 types of quartz sand we have used, and we have perfectly designed the packing density, and we got this compressive strength, and not required any special mixing facility. So usually these all parameters will increase the cost of the UHPC, but in these all parameters we have reduced the cost, and we can reduce this cost even more. We can reduce this Indian UHPC cost even more Yes, it's true. We can reduce the UHPC cost even more by adopting the following procedures. Binder can be replaced more cost-effective SCMs like ultrafine fly ash. Recently, we are getting ultrafine fly ash also. Ultrafine fly ash also excellent material. And comparing with ultrafine GGBS, here in this ultrafine fly ash, when you are using ultrafine fly ash, you have to use cement. Cement has to be replaced with ultrafine GGBS, and ultrafine GGBS, some percentage has to be replaced with ultrafine fly ash, so that you can reduce the costs more. And rises cash also we can use, and more optimization is possible. We can reduce the cement content more by using more trials. We can by developing a few more mixed designs. Steel fibers can be replaced with locally made steel wires. Locally made steel wires cut can be used steel fibers. So these are all parameters will be very, very helpful in reducing the overall cost of ultra high performance concrete. The future of Indian UHPC won't be imported. It will be intelligently blended from what lies beneath our soil. So these are the publications which we have done on this work. In International Structural Engineering Conference in Germany, we have presented 2 papers. And in national conferences also, we have published several papers. And these are all Scopus indexed papers. These are the references. Thank you. Now, if you have any questions, if you have any doubts, please you can raise.
Hello.
Sir, please.
Hello. This is Rajamane speaking.
Yes,
And
please, sir.
I want to make some important suggestions and also points for the, not only for the speaker, for the audience also. Okay,
please.
As all of you know, I worked on this material in SCRC in 1980s and 1990s.
Yeah, excellent, sir.
We have done even M350 also. Okay.
Yeah.
Now coming back to the presentation is very good, excellent. There is no problem at all.
Yes,
excellent presentation. Everything is very nice. Only I want to add some more points here. Okay, 2.36 mm, that is size of the aggregate. So much less is not necessary to be adapted for up to M150.
Okay.
When M20, 120 it is not necessary. We can go for higher size of the aggregate. Still will get that level of tank. Because okay, that's what I wanted to mention him and important. But most important is when you look at those aggregate should be stronger aggregate, not general aggregate which are due for M60.
Yes.
It should be known, kept in the mind.
Failure will happen.
That's what I want to keep it in the mind. Okay.
Yes.
Even if you up to 120, don't bother too much about the size of the aggregate of 2.6 is not valid. Not necessary. When you go more than 180 on 160 above, the size of the aggregate becomes very critical because of the homogeneity has to be built in the matrix. Homogeneity is very important word for the aggregate size. Okay, that is one point. And 30% silica fume is not required up to 120 or 100 and 120. Not required because we can increase the